Okay, so rational zero theorem is kind of like an extension of integral zero theorem. Integral zero theorem helps us find a factor of our polynomial by testing the constant. And that's only for polynomials with leading coefficient of 1. So what do we do when the leading coefficient is not equal to 1? Well, we have to use rational zero theorem. So we're saying, suppose we have a polynomial, and it has some kind of integer coefficients for the terms. And we have x equals b over a, so some fraction that is a 0 of the polynomial, where a and b are integers and a does not equal 0. So here's the idea. B is a factor of the constant term. A will be a factor of the leading coefficient. And all polynomials that do not have leading coefficient of 1 will have some factor, at least one, maybe more, in the term ax, in the form ax minus b. So do you guys remember how sometimes we have factors like this? That's what I'm talking about. So anytime we have a polynomial with leading coefficient that's not 1, basically this is just saying that at least one factor needs to be a fraction. That's what's going to happen, because I'm going to get something like this. Okay, so how do we figure out what these possible lists of factors are now? So anytime I see a polynomial, I'm still going to look to see if maybe there is a common factor that can be taken out. In this case, there isn't. So we're going to start with factors of the leading coefficient. And we're also going to do factors of the constant, which is 6. So factors of the leading coefficient, that would be 2. Factors of the constant, 6. So what are all the combinations of things that multiply to give us 2? Positive 2. It's pretty easy, right, Matt? 1 and 2 is one of them. There's one more combo that gives us positive 2. There we go. Okay, so that's our list. Surwa? The constant is negative 6. I was just testing you to see if you're awake. So all possible, yeah, Keaton?
I was wondering, like, the factors, could we write plus and minus 1, plus minus 2? Or would that be wrong?
We will write that eventually, yeah. I'm showing this process right now, but you can definitely do that, yeah. Factors of the constant. So I can have, so like Keaton said, I'm just eventually, hopefully we can get to the point where we'll just write a list here, right? If you need to, you can write out the combinations, right? We have 1 times 6, we have negative 1 times negative 6, or sorry, we have 1 times negative 6, because we're trying to get negative 6. We have negative 1 times positive 6. We have 2 times negative 3, and we have negative 2 times 3. So here's the full list. We have plus minus 1 and plus minus 2, as Keaton mentioned. We have plus minus 1, plus minus 2, plus minus 3, and plus minus 6. To get the full list of possible factors of our polynomial, we have to do combinations of these two things. So possible factors of p at x will be generated by doing all possible combinations of the constant term factors over the leading coefficient term factors to get something in the form of b over a. So constant factors over leading coefficient factors. I'm just going to use LC for leading coefficient. All right, so how does this work? So basically, I'm going to take each of these, and then I'm going to put them over each of these. What happens when I do 1 over 1? What do I get? Negative 1 over 1. Negative 1. Negative 1 over negative 1. Okay, so any way you spin it, I'm getting positive and negative 1 out of doing 1 over 1, right? Or negative 1 over positive 1. Okay, let's do 1 over 2 now. If I do positive 1 over negative 2, I'll get a negative half. If I do positive 1 over positive 2, I'll get a positive half. There's no other way that I can get different things, right? So I'm going to get either positive or negative half from doing 1 over 2. So I've done 1 over each thing here. Now I'm going to do 2 over each one of these. So 2 over 1. Any way I put it, no matter if I do negatives or positives, if I do 2 over 1, I'm getting possible negatives or positive versions of 2, right? What if I do 2 over 2? I just get 1, right? So no matter what I do, combinations of this, positives and negatives, I already have this covered in the list, right? I don't need to write it again. Okay, so 2 over 2, that's just equal to 1. So I've already got that covered. Okay, next one, 3 over 1. Again, I can have negative 3 over negative 1. I can have positive 3 over negative 1. Either way, I'm going to get back all possible positives or negatives of 3, right? Just 3 over 1. Okay, the next one, 3 over 2. I can have positive and negative combinations of that. So I'm going to add that to my list. Okay, last one, we'll do 6 over 1. Of course, that's just going to give me back 6. And of course, I can have different positive and negative combinations of that. And then the last one is 6 over 2. What's 6 over 2? So no matter which way I put it, I can do a combination of positives and negatives. I already have that in my list. So I don't need to write it again. So here's all of our list of possible factors. Rational zero theorem says that for sure, I know one of the factors will be either positive half, negative half, positive 3 over 2, or negative 3 over 2. Because the only way that I can have a leading coefficient that's not equal to 1 is to have a factor in this format. I have to have one of these fractions as a factor. So I could use that to my advantage, and I could just say, I'm just going to do tests just with the fractions. Or if I don't want to deal with doing synthetic division with fractions, I can test all the other whole numbers first, and maybe that will be easier for me. If I feel comfortable doing synthetic division with fractions, then go for it. You only have two sets of fractions here, so it might be quick to test. I usually just, with my class, I'll do like whole numbers because I find like synthetic division's a bit easier. Sorry guys, I'm trying to move to make this quieter, but okay. So whatever you want to do, you can choose. The first thing, of course, we want to create the possible factors, then we'll do the tests. If you want to test fractions, you can test the fractions. The test will obviously be a little bit more tedious with fractions as well versus whole numbers. So you'll have to weigh the pros and cons there and decide what you want to do. I'm already seeing, I don't think 1 is going to do it, but I'm thinking maybe negative 1. Maybe not, but we'll see. So actually, yeah, probably not, because this gives me negative 2 minus 1 minus 6, which will be negative 9 plus 13. So that gives me 4. So not a factor. That's okay. We'll try another. 1 is not going to work, right? Because I'll get 2 minus 1 minus 13 minus 6. That's going to be a bigger negative number. Let's try negative 2. I feel like positive 2 is not going to give us like enough to sort of like outweigh. Actually, I don't think positive 2. I'm just trying to think. Don't know if positive 2 or even negative 2 will work for us here. Let's try negative 2. Okay, in many of your calculators, by the way, there is a way that you can input an equation with x's, and then you can evaluate it for a bunch of different x values. So that can be really helpful for doing your tests. It's different based on your different calculators. So if you're interested in that, I can help you try to figure it out, or you can always look up a YouTube video, like how do I enter in an equation and evaluate for a bunch of different x's. Keaton? -2? Oh, it got 0? Okay, perfect. There we go. I didn't think it was going to work. X plus 2 is a factor. Okay, if I didn't get it, I would continue. I would do +2, -3, and so on. Let's divide. So once I've figured out the list of possible factors, pretty much everything else is the same, right? I do the tests, I do the division. I may have to do like trinomial hard factoring. Well, I will have to do hard factoring for trinomials if I find a whole number here, right? Because I'll get a result that has a coefficient in front of the x squared term. So I'll have to do hard trinomial factoring eventually here. So 2, -1, -13, -6. We will multiply and then add. Okay, do your division quickly here. I'll give you a couple seconds to do that. If you've done it correctly, you should be getting 0 at the end. Which I did, so that's good. So that means we calculated our factor correctly, and that means we used the right number here, means we did the division correctly. So remainder, constant, x coefficient, x squared coefficient. Now we're going to just finish up the factoring here. So last step is to do the factoring process for p at x. So don't forget the divisor. It's x plus 2. And then times the quotient. Get that from each of these. Now we're going to have to know our trinomial factoring. We're going to have to know how to factor hard trinomials. This is no longer an easy trinomial, right? I'm looking for two things that multiply to what and add to what. What do we have to do here if the coefficient is not 1? Kenzie? So -3 times 2, right? Okay, so I do a times c, so it needs to multiply to a times c, which is -6, and then it will still add to the same thing, so it adds to the middle term. So what are our numbers? Serena? I can't put these right into the brackets right away like I normally do. I will put them in and we will do grouping. Not my favorite method of factoring, but probably the most widely known by you guys. So I'm going to put -6x, that's my first number, and my second number is 1, so I'll put plus x minus 3. These should add back up to this. Okay, some of you guys probably already know this process. This is the last time that I'm going to go through this process slowly, because this was grade 10 and also grade 11, right? I would expect that people know how to do this by now. So we're going to factor by grouping. So first group, we need to common factor. I'm going to get a 2x taken out of those first two terms there, 2x squared and -6x. I'll be left with x minus 3. Second one here, I think the only thing that we can really take out from x and -3 is positive 1. So take out the number with its sign when you're factoring with grouping like this, and we'll be left with x minus 3. I now know that I've done this correctly and I can continue with this process. because these are the same. If I don't get two of the same brackets, something went wrong somewhere, or it's not factorable. That's possible, could not be factorable. And we will do our final step here, take out the x minus 3. We will be left with 2x plus 1 in the last bracket.
Does it matter what order you do?
You guys tell me, does it matter? What does everyone think?
No.
It's like 7 times 1 times 3, or 1 times 3 times 7. I'm going to get the same thing, right? Okay, so there is our factored form. Are we asked for solutions here? Factor to solve. So we're going to set this equal to 0 to solve and write the solutions. And I want you guys to notice and compare our solutions to the list of possible factors that we had created above. So our solutions, -2, +3, making sure I switch the sign. What's the solution for something that looks like this? 2x plus 1? Okay, -½ right? Make sure you switch the sign, just like you do for the others. If you're not sure, what do? Set it to 0 and isolate. Okay, you'll get -½ Okay, what do you guys notice about all the list of possible factors and the x-intercepts that I ended up getting here? What's the connection? Sam? Every single x-intercept falls on this list somewhere. And that's not a mistake. That's going to happen every single time with every single polynomial that you factor, because I listed all of the possible factors. And they will all be contained in that list. Okay? So this is the process of factoring. Of course, if I'm just solving, I could, if I wanted to, maybe just test every single number in there and just find the x-intercepts that way. If I'm asked to fully factor, maybe I need to go through a bit more of a process to do that. But yeah, every single binomial you get will be represented back in this list here. That's why it doesn't matter which factor I find. If it's different from the factor you find, we'll all get those same 3 binomials in the end. Okay, questions on this one? Can I clarify anything? Serena?
How do you know that you have to do this process? How would you tell someone?
So I would always try grouping first for something like this. I can already see if I take out an x squared here, I'm not going to get the same thing in that second one. So that's where those fast factoring methods come in. I need to try out some of those fast factoring methods, go through the methods in my head. This is the last resort. If I can't do any fast factoring methods, if I can't do grouping, there's not much else I can do other than this process to factor. Zach?
So when you're doing the factoring, and then you did 8 times c, why did you just do like what wasn't added to -5 and -3 instead of like times and c?
Yeah, so that method that you're talking about is only when the coefficient of x squared is equal to 1. The coefficient of x squared is equal to 2 here, so it's a bit of a different factoring process. This would be called like a hard trinomial, whereas something where x squared is coefficient of 1 is like easy factoring. Or like quick factoring, right? Where we can just find what multiplies to c and b and then put them right in the brackets right away. Okay, so if x has a coefficient, x squared has a coefficient, I should say, that's a hard trinomial process. Other questions? Okay, so we are working on an assignment